Today I'm going to be discussing power supplies and power supply stability. And I want to look at a few different common types of power supplies I suppose you might have laying around and get an idea for how they compare with each other as far as stable, how stable they are. So before I get into the circuit, which is very, very simple, I want to say what I mean by stability. And a perfectly stable power supply would be one where the voltage does not change at all with time. So, I'm drawing kind of like an oscilloscope window here, where the voltage would just be a flat line. That's what we want. You set it to 5 volts and it gives you 5 volts exactly. But some of the power supplies we'll be looking at, and realistically, might have a periodic spike or ripple. They might be, or let's see. They might be something more like this. Let's see. Okay, and when you're selecting power supply, ideally you want this, but in the real world you might be forced to shoot for the next best thing, which might be 1%. If you can get a 1% ripple voltage compared to the supply voltage. So when I say ripple voltage, I mean if you were to measure the ripple voltage, it would be how wide, and I usually do it with a Sharpie, but let me grab a pencil. So I have 2 different colors. If you were to measure, from here to there, the lowest point to the highest point, that's your ripple voltage. And we want this to be small. But we also want to compare it to our power supply. So you would expect like a 30 volt power supply to have a little bit higher ripple voltage than a 3 volt power supply, because a 1 volt ripple on a 30 volt is hardly anything, but a 1 volt ripple on a 3 volt power supply would be completely unusable. So you have to take that into consideration. And one of the things you might do is kind of get a percentage ripple, which would be, what's your ripple voltage? That's kind of, the Sharpie's great, but if I had a thinner Sharpie, I might take a look at that too. But your ripple voltage divided by your just power supply, I don't know, VN or something. And that'll be a ratio or a percent, like a percent ripple. Okay, so I'll be doing that throughout the video. So let's take a look at this circuit that I made. And all I have going on here is 2 power supplies that are separate, except I have their ground wire connected for simplicity of, that way I only have to move the oscilloscope. This is an oscilloscope probe. I only have to move up from here down to there to switch which one I'm looking at. I guess I could hook them up simultaneously. Maybe I'll do that. Anyway, I'll draw the circuit. It's very simple. We have some power supply VN, and then I'm just putting it through a load resistor and then right back. Okay, So you can call it a circuit if you want, but it's pretty simple. This is the test point. Let's see. No, that's not the test point. That's ground. This is where I'm testing the output voltage. So between here and ground. Between between there and ground is V out. The first power supply I wanted to take a look at was this 12 volt wall wart, I call it. It's really just a transformer and some circuitry on the inside to convert it to DC. It's 12 volts, 2 amp rating. We'll see how it really performs. I have the oscilloscope connected through a 1K resistor, and let's take a look at the scope. You can see this ripple voltage, and well, actually I have it really zoomed in. Let's see what it looks like on normal DC coupling. And there it is. So just looking at it, it looks pretty stable, and I would say it's not bad. But if we wanted to characterize and measure the ripple voltage on this, we're going to have to change its coupling. We'll do it, let's see, DC coupling, change it to AC coupling, and that pretty much just runs it through a capacitor to block all the DC offset. And now we can scale it up, and what's left is the ripple voltage. So real quick back here, explaining DC AC coupling. Whenever you do AC coupling, it takes every bit of voltage that doesn't change, and that would be everything from the lowest peak down to ground, and gets rid of it. Okay, and so for this one you would just see that. All right, that's the idea. And then we can scale it up on the oscilloscope, and well, I have it set to 50 millivolts per block. I would say, generous estimate, I don't know, 80, maybe 100 millivolts. Ripple voltage, we have this kind of smaller ripple up and down, but then we have this larger, like really dramatic spike, and that's what I'm going to count as the ripple voltage. And I want to write that down. Let me go to the next page. So this is the 12 volt power supply with a 1K. That's supposed to be a W and a slash for width, with a 1K resistor load. And we're seeing, I said, about 100 millivolts of ripple. How good is that? Well, 100 millivolts, if we do our percent ripple, 100 millivolts, which is like 0.1 volts divided by 12, and you could multiply by 100, I suppose. That's 0.83%, or 100 millivolts is 0.83% of the voltage input, 12. That's pretty all right. We want to say percent ripple, I guess, is equal to 0.83%. 0.83%, not 0.83, 0.83%, less than 1%. By my standards, that's very usable. Let's take a look at this other one. This is a phone charger, it has 18650 lithium cell, rechargeable cell, but it also has a step-up circuit, because remember lithium cells are 3.7, and so it needs a step-up circuit to take it to 5 volts to charge a phone. We'll see the effect of that. I'm just going to switch my probe over to the other one. I have a different resistor. It's a 330 ohm, but that's because it's a 5 volt load. So it wouldn't be fair to put a 1K on both sides, because this is a 12 volt and this is a 5 volt. So, you know, that's not a perfect ratio, but it's better. And let's see what's going on the oscilloscope. 15 millivolts. I don't think I have it connected or something. Let's see what's going on. I do have an AC couple. Let's DC couple those. That is not what I was expecting. Let me take that load resistor out. Huh. Oh, I guess I have to. Oh my. Millisecond. What would be a 10? A 10 millisecond. Oh, that must be our problem here. I don't think it was plugged in. Okay. Yeah. We'll go back to AC coupling so we can see. I have it way zoomed out. Alright, that's what I was expecting to see. This looks a lot different than the AC with the transformer, the 12 volt we were looking at. This is coming from a battery, but it has to go through a voltage step-up circuit first, and it's a digital circuit, and so it's creating this triangle waveform as it, like a, you know, it's a switching voltage supply. So that actually makes it a little bit cleaner to measure what the ripple voltage is. And it's on 10 millivolts peak to peak. Or sorry, it's a 10 millivolt grid. So, you know, that ripple is peak to peak 40 millivolts. So the 5 volt. Oh, let's put the load resistor back in. I took it out when we were doing diagnostic, and that changed everything, so now we have to, it's messier because we have an actual load, 20 millivolts, so now that's more like 80 millivolts peak to peak. So that's a 5 volt with a 330 ohm resistor, and I'm calling that 80 millivolts. Do some math. 80 millivolts over 5 volts is, this time the percent ripple is a lot higher. It's 1.6%. So yeah, 1.6% ripple. I mean, that's still low, I suppose. I said 1% ripple is a decent rule of thumb. It depends on the application. For a phone charger, 1% ripple. Who cares? 1.6. It could be 5% ripple, and it probably wouldn't matter. But for analog circuitry, yeah, you'll see that. That might mess things up for you. So, how do we take care of this? We can throw in a huge capacitor, and that's what I'll do. We'll see what happens when we put a capacitor in. So, electrolytics have polarity. Gotta be careful with that. I put it into the 5-volt circuit, and you can take a look at the oscilloscope. I haven't changed the setting at all. There's without cap, that's with the cap. Big difference. Of course, it's a 1,000 microfarad capacitor, so that's kind of a large capacitor. Well, let's measure it now. It's still there. It's just smaller. Ugh. That's a 2 millivolt grid. So I'll call it 4, 5 maybe. I mean, generous 6 at most. So with the capacitor, 6 millivolts. I mean, that's nothing. .12%. So that's hardly anything. For fun, we can throw it in the 12-volt circuit too, just to see what that looks like. That's real messy. Okay. That's all right. Doesn't have to be clean. 5 millivolts grid. We'll call it 20 at most. So 20 millivolts is 0.02 divided by 12. And that's 0.16%. Pretty close, actually. But it gets better. The standard to compare to, I suppose, and what's hard to beat is a battery, because it puts out DC current like no other. It's all chemistry, and there's no switching going on, or sinusoidal waveforms or any of that going on inside a battery. So the output is very, very stable as far as ripple goes, and you won't even be able to see it on an oscilloscope. It's so small. If it exists at all. So that's great, but the bad thing about batteries, of course, is that you can't hook up a circuit for 12 hours on end and expect it to give out the same voltage, whereas something like this, at least it'll continuously step it up to 5 volts until it can no longer do so. Or like this, you could have this plugged in 24/7, and it'll always put out about 12 at the cost of some stability. So I had some fun with this. I hope you guys found this useful, being able to take a look at a power supply, kind of compare it with other power supplies. Oscilloscope is a great tool for doing that. Remember, it's important that you test it putting a load resistor in, because without the load resistor, it won't drain capacitors that are in the power supply circuits. Like it's basically a false a false reading. You have to measure how the power supply performs while it's doing work. You can't measure it how it performs whenever it's not doing work, you know. So yeah, I had some fun with this. Hope you enjoyed it. If you liked the video, please give thumbs up and subscribe to my channel. If you have any questions about like power supplies and such, leave them in the comments below. If you have ideas for other stable power supplies to use, I'd love to hear those suggestions. Or what other techniques do you use to measure the effectiveness or stability of a power supply? Other than that, thanks for watching. See you next time.